Welcome back to lecture 16, Continuity and Differentiability of a Function in One Variable. In the lecture 15 and 14, we have already studied basics of function, intervals and number system. And in lecture 15, we have studied how to find the limit of a function in one variable. For that, we have discussed several cases and we also saw some important limits. Today, we will study some another properties of a function like continuity and differentiability of a function. So let's start. Continuity. A function fx is said to be continuous at x equal to a if left hand limit of fx exists and right hand limit also exists and both are finite and both are equal, and this value is equal to the value of function at x equal to a. Or in another language, I told you if left hand limit and right hand limit both exist and finite, then limit extending to a fx exists. And if this is equal to f of a, then a function fx is said to be continuous at x equal to a. Now, this is a very important point here. X equal to a. Can we check the continuity of fx at any x equal to a? No. The general answer is no. That point A is very important. For continuity of fx at x equal to a, we have to get immediate neighborhood of a. What is the meaning of this? Suppose y equal to log x is given to you and y is equal to fx also. And if you see what is the graph of log x, you can follow lecture 14 for it. I told you this is the graph of log x when base is greater than 1. Here base is exponential, so it is greater than 1. And it is defined for all x greater than 0. But if you are interested in the continuity at x equal to minus 2, then it is meaningless because we don't know the value of this function in the immediate. Immediate means very near to that point, in very small distance. Means we cannot check the continuity of fx at x equal to minus 2 because we don't know the value of fx in the neighborhood of minus 2. So continuity at minus 2 is meaningless here. Meaningless here. Suppose you have another example. Y is equal to fx equal to 1 upon x minus 1. If you do the graph, draw the graph of x equal to 1 upon x minus 1, the x equal to 1 will be the neighborhood of it. It will look like this only. If you are interested in the continuity of x equal to 1, then the neighborhood of 1, at 1 it is tending to infinity, at 1 y is tending to infinity, so it will work as an asymptote. But in the neighborhood of 1, right hand neighborhood 1 plus h, you will get some y. You will get some y. That y may or may not be finite. It depends. You will get some value. It means it is defined in the neighborhood of 1. And defined means you are getting the value of fx in the neighborhood of 1. That value can be infinity also or any value. But in this case, you don't know the value in the neighborhood of minus 2. But in this case, in the neighborhood of 1, you can find the value of fx. That is right hand neighborhood. You can draw it is in the third quadrant also. But I am taking only one neighborhood here. It means what is the meaning of this statement? That continuity of a function is the property of interval. And is meaningful at any point x equal to a only if the function has graph in the immediate neighborhood I have already discussed in lecture 15 of x equal to a. Not necessarily at x equal to a. Means the function is defined at x equal to a, it is not necessary. But for checking the continuity, we have to get the value of function in the neighborhood of x equal to a. If the function is defined at x equal to a and it is equal to the value of function, then the function will be continuous. That is a separate thing. But for first step, to check the continuity, that the graph of function should be in the immediate neighborhood of that point. And the value of that point, the value of function of that point is the secondary thing. If this is equal to that limit, then the function is continuous. That is secondary thing. Okay. Directional continuity. Directional continuity means if you are able to find the continuity of a function in right hand or left hand directions. Suppose a function fx has left hand limit is equal to the value of function at x equal to a, and limit x tending to a plus fx equal to fa. In this case, I'm taking here another point. Suppose this is a b plus and this is your fb. At b I am checking it and a I am checking here. In this case, it is called left hand continuous, left side continuous at x equal to a. And in this case, you have right hand continuity at x equal to some another point b. Means the continuity from one side is called directional continuity. It is useful when you are finding the continuity of a function in any interval. Suppose you are interested in the continuity of a function in any interval. Take case 1. In the closed interval, a function fx is said to be continuous in closed interval a comma b. In the previous definition, I have seen the continuity of function at any particular point x equal to a. But in this case, I am studying the continuity of a function in any closed interval a comma b. A function fx is said to be continuous in closed interval a comma b if for any c belongs to open interval a comma b. For any c belongs to open interval a comma b, limit x tending to c fx equal to fc. Means for every interior point inside this interval, function is continuous. And at boundary points, suppose first boundary point is x equal to a. In this case, at x equal to a, if you draw a simple graph of this function, like function is this one. So at x equal to a and x equal to b, x equal to a, you can find the right hand limit because a plus h belongs to in this interval, but a minus h does not belongs to in this interval. So at x equal to a, we will get directional continuity, means right hand continuity, because right hand value of x equal to a, it is taking place in this closed interval. And at x equal to b, we cannot find the right hand limit because b plus h is going to be outside, but b minus h at h is very small and always positive. B minus h belongs to this interval. In that case, you will get the left hand limit of fx at x equal to b. In this case, this is called one-sided continuity or directional continuity. This is a right side continuous, this is left side continuous at the boundary point, but for any interior point it is continuous, means LHL equal to RHL equal to the value of function at that point. Similarly, in open interval a comma b, you do not to check continuity at the boundary point. In that case, for any arbitrary c belongs to open interval a comma b, limit x tending to c, fx equal to fc for any c, for any arbitrary c, or you get for all arbitrary c, for all c, for all c, all c. For every point, this property must be satisfied. Or any arbitrary, then c can be any value between open interval a comma b. Then this function is continuous in open interval a comma b. So all points should be taken here. Next is, when a function is not continuous, then it is said to be discontinuous. So discontinuous can be taken by many cases. Like I'm taking first discontinuity is removable discontinuity. Removable discontinuity. Another name is missing point discontinuity. Missing point discontinuity. In this case, limit x tending to a fx exist. Means, what is the meaning of this? Limit x a minus means left hand limit exist, and x tending to a plus fx means right hand limit exist. Both exist and equal. Both exist, finite and equal. But limit x tending to a fx is not equal to fa, but is not equal to fa. Or limit x tending to a fx exist, but fa is not defined. There can be two cases. First case is fa is defined, but it is not equal to the value of limit. Second case is limit exists, but fa is not defined. Then in this case, discontinuity is called removable discontinuity. Removable discontinuity. Take example for this. Example based on removable discontinuity. Check continuity at x equal to 0. Fx equal to sin x by x when x is not equal to 0, and it is 2 at x equal to 0. if you find the left hand limit, right hand limit, take the left hand limit. X equal to 0 minus h. I told you left hand a minus h, and a is given to a here. A is given to 0 here. Then it will be limit h tending to 0, f of 0 minus h equal to limit h tending to 0. It is not equal to 0. It is not equal to 0. It is less than 0. So you have to pick the function h sin x by x and put x equal to 0 minus h upon 0 minus h. So it is limit h tending to 0, sine minus theta is minus sine theta. Minus sign will cancel out. This value is 1, I have already told you. And if you find the right hand limit, x equal to 0 plus h, then it will be limit h tending to 0, f of 0 plus h, and it is again not equal to 0. So it is limit h tending to 0, sine 0 plus h over 0 plus h, and it is again 1. So left hand limit equal to right hand limit, both are equal and finite, and it is equal to 1. So limit x tending to 0, fx exists. Now we have to see the value of function at x equal to 0. At x equal to 0, the value of function is 2. Means limit x tending to 0 fx is not equal to f of 0. So function is discontinuous at x equal to 0. But why the name is removable? It is a removable discontinuity because we can remove this discontinuity. How can we remove this discontinuity? Because there is a possibility to define the function in such a manner that limit x tending to a fx equal to fa. There is a possibility. So how we can make this function as a continuous? If we replace this value by 1, then this discontinuity can be removed. So it is called removable discontinuity because we have a possibility to define a function in such a manner that the value of function at point is equal to the limit of the function. Take another example. Take another type of discontinuity. Second is non-removable discontinuities. We have non-removable discontinuity. We have two cases here. First is jump discontinuity. Jump discontinuity. In this case, limit x tending to a minus fx means the left hand limit, and limit x tending to a fx means the right hand limit. Both exist, very good, and finite, but not equal. Means limit x tending to a minus fx is not equal to limit x tending to a plus fx. This is called jump discontinuity. Both exist and finite but not equal. It means limit does not exist. It means, or you can say that limit x tending to a fx does not exist, but does not exist due to this sense only, when both LHL, RHL exist and finite. So I think no need to write this. Only write LHL and RHL both exist and finite but not equal. Then this discontinuity is called jump discontinuity. Take example for this. Jump discontinuity example. Example 2. If we take a function fx equal to greatest integer x at x equal to 5. I told you in the limit lecture that the greatest integer function is not continuous at integers, or limit does not exist at integers. We can see that. So left hand limit will be x equal to 5 minus h. Limit h tending to 0, f of 5 minus h equal to limit h tending to 0, greatest integer 5 minus h. And what about h? H is very small but always positive. It means you are less than 5. Less than 5 means the least integer is the left integer to 5 minus h will be 4. This limit is existing because it is a finite value also and existing. What about RHL? X equal to 5 plus h, then limit h tending to 0, 5 plus h greatest integer. 5 plus h means you are greater than 5, then what will be the left integer for it? It will be 5. Both limit are existing and finite, but left hand limit at 5 is not equal to the right hand limit at 5 of fx. So this function has jump discontinuity. You can see by graph also. If you draw the graph, it is 4, it is 5. At x equal to 4, x equal to 4, in the left hand limit, you are checking the discontinuity at 5. At 5, you are getting left hand limit at 4. Left hand limit at 4. And at right hand limit, you are getting value as 5. You can see by graph also, it is jumping at x equal to 5. It is jumping at x equal to 5. If you see my lecture 14, you can see the greatest integer function graph. So left hand limit is here and right hand limit is here. So it is jumping. So it's a jump function. You can see by one more example, jump discontinuity. Very simple example I am taking here. Example 3 on jump discontinuity. If you take fx as x plus 2 when x is lesser than 1 and it is 5x when x is greater than equal to 1. Check continuity at x equal to 1. If you find the left hand limit, then it will be x equal to 1 minus h. Limit h tending to 0, f of 1 minus h. The value is less than 1 obviously. So x is less than 1. It means we have to take the function as x plus 2 and the value of x is 1 minus h plus 2. So if you apply h equal to 0, you will get 3. What about right hand limit? X equal to 1 plus h. It means it is greater than 1. So limit h tending to 0, 5 and the function will be 5x and x will be 1 plus h. If you apply h limit, it will be 5. So both limit are existing and finite, but they are not equal. So 1 minus fx left hand limit of function at x equal to 1 is not equal to right hand limit. It means that this is a jump discontinuity, non-removal discontinuity, and in the non-removal discontinuity is a special kind is jump discontinuity. If you draw the graph, you can see it. X plus 2 will look like this only, and up to x equal less than 1, the graph is this, and at it is x equal to 1 point, and in the neighborhood of if you draw the graph of x 5x will look like this only, but you are interested at from x greater than equal to 1, x greater than equal to 1. At x equal to, in the neighborhood you are left in neighborhood you are getting 3, but in the right neighborhood you are getting the value as 5. At x equal to 1, if you see at x equal to 1, the value is 5. So at x equal to 1, we are getting circle here because it is jumping at 5 at x equal to 1. But in the neighborhood of left neighborhood of x equal to 1, the value is 3. And the right hand neighborhood and the value at x equal to 1, the value is 5. So the graph is jumping here. This is called jump discontinuity. The another type of discontinuity is essential discontinuity. Essential discontinuity. In this case, In this case, at any point x equal to a, at any point x equal to a, LHL means left hand limit or right hand limit or both, means LHL and RHL both, does not exist, does not exist, or infinite, or infinite, or infinite. In this case, the discontinuity at x equal to a is called essential discontinuity. For example, if we take f x equal to x plus 2 when x is greater than equal to 1, and 1 upon x minus 1 when x is less than 1. I'm taking left hand limit here. So left hand limit is going to be 1 minus h. It is 1 minus h means less than 1. So limit h tending to 0, f of 1 minus h. F will be picked as 1 upon x minus 1. So 1 upon 1 minus h minus 1. It will be limit h tending to 0, 1 upon minus h. As h tending to 0, it will go to minus infinite. It means the one of the limit is tending to minus infinite. So this type of the function will be discontinuous. The function will be discontinuous here, and that point at x equal to 1, at x equal to 1, that fx is discontinuous, function is discontinuous, and has essential discontinuity. Essential discontinuity. So these are some important types of discontinuity. Now, theorems and results on continuity. These results and theorems are very important in better understanding of continuity. So first result is sum, difference, product, quotient and quotient. Quotient of two continuous functions at any point, suppose x equal to a, are always continuous at x equal to. If two functions are continuous at x equal to a, then their sum, difference, product and quotient will be also continuous. Provided in the case of quotient, suppose the functions are fx upon gx, then at x equal to a, GA will not be equal to 0. GA will not be equal to 0. Result 2 is, suppose fx is continuous. Fx is continuous at any point x equal to a. And if you add any discontinuous function at x equal to a, gx is discontinuous at x equal to a, then their sum will be also discontinuous at x equal to a. Sum or difference will be discontinuous at x equal to a. But in the case of, suppose f is continuous, fx is continuous at fx is continuous at x equal to a, and gx is discontinuous at x equal to a, then product fx into gx at x equal to a can be, or maybe continuous at x equal to a. Means we cannot say anything, or may not be, Means in the case of product, we cannot claim anything if one function is continuous and another is discontinuous. But in the addition and subtraction, we can say that the output will not be continuous. It will be discontinuous only. Then you have two discontinuous functions. when you have two discontinuous function, then let fx and gx both are discontinuous at x equal to a, then fx plus minus gx will be also discontinuous. But fx into gx may or may not be continuous. Okay, I am going to do correction here. Will be also discontinuous. Here also may or may not be continuous. May or may not be continuous means in the case of both discontinuous functions, we cannot make any comment. We cannot make any comment for the output of these two functions. This output can be addition, subtraction, or multiplication or division. For example, if you take any function fx as a greatest integer x at x equal to 1, it will be discontinuous. You can verify left hand limit and right hand limit are not equal. If you take another function gx as a fraction function at x equal to 1, it will be also discontinuous. Anyone can check the left hand and right hand limit, and you know that the gx can be written as also x minus greatest integer x, and due to this function the output will not be continuous. If you add both fx plus gx, both are discontinuous at x equal to 1, but if you add x plus fraction function x, a greatest integer x plus fraction function x, it will become x, and the output is continuous at x equal to 1. Why this is continuous? This is a polynomial. The next result is based on this. If you check the left hand and right limit at x equal to 1 and find the value at x equal to 1, you will get the function is continuous. The output function is continuous. Suppose this is output is hx. You check the continuity of hx at x equal to 1, you will see that the function is continuous. Fifth property I have, every polynomial function is continuous at every point of real line, and polynomial function is defined as a naught x to the power n plus a1 x to the power n minus 1 and so on plus an. For every x belongs to real number, this function is always continuous. The sixth result is every rational function, take fx upon gx, this will be a rational function provided gx is not 0 at any given x, is continuous at every point where its denominator is different from 0, means denominator is not 0. Seventh property is logarithmic function, exponential function, trigonometric function, inverse trigonometric functions, inverse circular functions, trigonometric functions, modulus function, are continuous in their respective domains, are continuous in their respective domains. Next properties I have. These properties are related with the closed interval. Properties of fx in closed interval a comma b. First is, if a function fx is continuous in closed interval a comma b, then it will be bounded. Bounded functions means you have a max value and min value of fx. You have a max value and min value of fx. Then this function is called bounded. Or it is strictly less than, means we cannot claim that this is equal to m, but we will get some finite upper value for this. Finite upper value for this. Then this function is called bounded function. Second is a continuous function whose domain is some closed interval must have its range also. Domain and range I have already discussed in lecture 14 in the closed interval. In the closed interval. And the third is, if FA and FB have opposite signs, means at boundary FA and FB has opposite signs, opposite nature, then their product must be negative. Then there exists at least one solution C, always odd numbers, always in odd number. At least means that there can be 1, 3, 5, 7 solutions like this of the equation fx equal to 0 at fc equal to 0. Means we have a solution C which belongs to open interval a comma b, for which the equation fx equal to 0 is satisfying. And the fourth property I am writing here, if f is continuous in closed interval a comma b, then f inverse is also continuous. Then f inverse is also continuous. Okay, there is a correction. Fx is bounded when it is less than equal to m. It can be also equal to m also. So bounded means fx is mod of x less than equal to m. Okay, so these are some important properties and results based on continuity. Let's see some examples. Example 1. Find the value of k so that fx is continuous at x equal to 0. and fx is giving you as here tan pi by 4 plus x to the power 1 by x when x is not equal to 0, and it is equal to k when x equal to 0. So if you see the question, the function is given to you continuous, means at x equal to 0 means limit in the left neighborhood at 0 is equal to the in the right neighborhood, means LHL, RHL both exist, and equal to x tending to 0 fx. And this value is equal to f of 0 is given to you because the function is continuous. And the value of function at 0 is given to you k. It means we have to find the k, and the limit is existing because the function is given to you continuous, so we can directly find the limit here. The limit is tan pi by 4. No need to check the LHL and RHL because the function is given you as continuous. It means LHL and RHL both exist and both will be equal. So if you put x equal to 0, you will get tan pi by 4. Tan pi by 4 is a 1 to the power infinity case. If you see, this is not exactly 1, this is approximately 1. So it is an indeterminate form of 1 to the power infinity. And for 1 to the power infinity, I told you this limit is equal to the limit x tending to 0. fx is tan pi by 4 plus x minus 1 into gx. If you see the lecture 15, you can see how to tackle 1 to the power infinity form. So k will be equal to limit x k will be equal to the e to the power limit x tending to 0 tan pi by 4 plus x minus 1 upon x. Now if you put the limit x equal to 0, it will be tan pi by 4. It means 1 minus 1 upon 0. So it is 0 by 0 case. 0 by 0 case means you can apply L'Hospital rule or expansion method. So L'Hospital means differentiate numerator and differentiate denominator. Both are differentiable function. Both can be both have derivative. So the derivative of tan is sec square pi by 4 plus x with respect to x, and derivative of 1 is 0 and derivative of x is 1. So if you now you can put the limit x equal to 0, it will be sec square pi by 4, and sec pi by 4 is a root 2, so square will be e square. It means k will be e square, so that this function will become continuous. Now the second question I have, find values of a and b so that fx is continuous. Or fx is given to you continuous, find the values of a and b, and the function is ax minus b when x is less than equal to 1. It is 3x when x is between 1 to 2, and it is bx square minus a when x is greater than equal to 2. So how to check the discontinuity or continuity at the given points? It is between 1 to 2. So you always see the continuity at the points where function is breaking. So it is breaking at 1 and 2. Or you can see the equality sign is there. At 1 and 2 we have equality sign. So we'll check the continuity at x equal to 1 and 2. So it is given that the function is continuous in this given domain. So limit x tending to 1 minus at 1 fx will be equal to limit x tending to 1 plus fx equal to f1. The first condition is given to you, and for x equal to 2 also it is given you. We will check at x equal to 2 later. See firstly at x equal to 1. So x1 minus, it means LHL at x equal to 1, I'm going to check left hand limit. It will be 1 minus h. Then I will tell you some shortcut also. So 1 minus h is less than 1. It means we have to opt the function h ax minus b, and you put x is equal to 1 minus h minus b. If you put the limit, it will be a minus b. What about RHL? X equal to 1 plus h, it is greater than 1. So we will take the function h 3x. 3 1 plus h will be 3. Now both are equal because the function is continuous. We want to make it means a minus b left hand limit equal to right hand limit. Both will be equal and it will be 3. A minus b will be 3. This is the first equation for it. Now you have to check at x equal to 2. It is also given continuous at 2. So left hand limit will be the right hand limit will be equal to the value of function at 2. Now at x equal to 2, left hand limit will look like x equal to 2 minus s less than 2. So limit h tending to 0 less than 2 means function will be 3x and x will be 2 minus s. So it will be 6a. And if you see at the right hand limit at x equal to 2, RHL at x equal to 2, it will be 2 plus h greater than 2. So limit h tending to 0. B greater than 2 means function will be bx square minus a. Any 2 plus h whole square minus a. So if you put h equal to 0, it will be 4b minus a. 4b minus a. Now equate both the equation LHL equal to RHL, you will get the second equation 4b minus a equal to 6. This is the equation number 2. If you solve a and b, if you solve first and second, you will get the value of a and b. I think a will be the 6 and b will be the 3. You can verify this. Now we have another shortcut method for this question also. What is the shortcut method? See, this is a very important shortcut method and it can be solved here only. These are our polynomial functions. So polynomial functions are continuous in the entire real line. I have already told you. So at x equal to 1, this is the value is less than 1. It means Rx equal to 1. We will get left hand limit and the value of function at x equal to 1 from here. So put x equal to 1 here. X equal to 1. So a minus b and put x equal to 1 here because we will get right hand limit from here. So put here also because the function is continuous. So first equation is this. Now for x equal to 2, put x equal to 2 here. It will be 6 and put x equal to 2 here also. So it will be 4b minus a. If the function is continuous, then in the continuous case, you can directly put the value in the left hand right hand limit. Even it is not given equality sign here, but you can put. Now if you solve a and b, a and b from these two equations, you will get the same answer. But this shortcut will work when the function is continuous. Now, what is the differentiability? One most important topic in the calculus. Differentiability or existence of derivative or existence of derivative. A function fx is said to be differentiable at x equal to a if limit x tending to a fx minus fa over x minus a exists and finite. Exist and finite. This is again a limit, so it's a left hand limit and right hand limit, both must be exist. In the case of derivative, these are called left hand derivative and right hand derivative. If we approach from left hand side, it is called a left hand derivative. So left hand derivative of function f at a is defined as, this symbol is for derivative and minus sign is defining left hand derivative. It will be equal to limit h tending to 0. You will put x equal to a minus h and h tending to 0. This can be reduced as f of a minus h minus fa upon minus h. If you put x equal to a minus h, you will get. And what about right hand derivative? Right hand derivative will look like f dash a plus, then in that case you have to put x equal to a plus h. It will become limit h tending to 0 f of a plus h minus fa over plus h, fa over plus h. If these derivatives, left hand derivatives and right hand derivative, both are equal and finite, both are equal and finite values, then fx is differentiable at x equal to a, at any point x equal to a. If what is the meaning of derivative in geometrical? Geometrically, fx is a differentiable. I'm giving you as a homework, you can see, at x equal to a, if a unique tangent can be drawn at this point x equal to a, at this point x equal to a. This is the differentiability at any point, but for any x, you can write for all x, if you write for arbitrary all x, then the d by dx of fx exists if it is right hand derivative for all x, fx plus h minus fx upon h is equal to limit h tending to 0 f of x minus h minus fx upon minus h. This is also called first principle. In general, we write like this. This is called first principle. This will work when function is differentiable at any point x. Now, you can put x equal to a or any fixed point. You will get the same result I have discussed. You can put any x equal to a. What is the relation between continuity and differentiability? Firstly, I am seeing at a point x equal to a. If a function fx is differentiable at x equal to a, then it will be continuous at x equal to a. But converse need not be true. Means if the function is not continuous at x equal to a, but the converse means if the function is continuous at x equal to a, then it need not be differentiable at x equal to a. But we have one result. If a function fx is not continuous at x equal to a, then fx must not be differentiable at x equal to a. For example, I am taking the converse part. For the converse part, fx equal to mod x, check continuity and differentiability at x equal to 0. So firstly, I am checking the continuity for this question. For the continuity, left hand limit, right hand limit we have to obtain. So for continuity at x equal to 0, so left hand limit will be x equal to 0 minus h. Then it will be limit h tending to 0, f of 0 minus h equal to limit h tending to 0, mod of 0 minus h And if you take the mod sign, it will be again plus h, and if you put h equal to 0, it will be 0. What about the right hand limit? X equal to 0 plus h, then limit h tending to 0 mod of 0 plus h, it is going to be again 0. What about the function value of f at x equal to 0? It will be mod of 0, it will be 0. You can see that the left hand limit equal to the right hand limit equal to the value of function at x equal to 0. It means the function is continuous at x equal to 0. The function is continuous at x equal to 0. Now check the differentiability. Differentiability of fx equal to mod x at x equal to 0. Now take the right hand derivative. So I told you the right hand derivative at any point is given as limit h tending to 0 f of a plus h minus f of a over h. So here I am checking at 0, so it will be limit h tending to 0 f of h minus f of 0 over h. It will be limit h tending to 0, f of h will be the mod h, f of 0 will be the 0 mod 0 will be 0 upon h. And h is again always positive value, so it will be h upon h. If we simplify, we will get 1. The constant, limit of any constant value is constant. So right hand derivative is plus 1. What about the left hand derivative? Left hand derivative is given at any a is a limit h tending to 0 f of a minus h minus fa over minus h. So at 0 it will be 0 minus h equal to limit h tending to 0 0 minus h minus f of 0 over minus h. So it will be limit h tending to 0 mod of 0 minus h minus 0 upon minus h. So it will be limit 0 h tending to 0 mod of minus h will be again plus h. So it will be the minus 1. It means left hand derivative is not equal to the right hand derivative. So fx equal to mod x is not differentiable at x equal to 0. We have some another approach also. If you see another approach like this, graphical approach and tangent approach. Differentiability of fx equal to mod x at x equal to 0. Graphical approach. If we draw the graph of mod x at x, this is the graph of mod x. At x equal to 0, you are getting a V shape. If you are getting a V shape at any point, then function is not differentiable. And another reason, if you see in the right neighborhood of 0, the slope of this line is tan 45 equal to plus 1 because it will be y equal to x. If you take in the right neighborhood, in the left neighborhood will look like minus x, then the slope will be minus 1. So at x equal to 0, if you draw the tangent, then the tangent have different slopes from the right and from the left. It means you are not getting unique tangent. It means function is not differentiable at x equal to 0. Now, how can a function fail to be differentiable? Fail to be differentiable. How you can check a function is not differentiable? There are three possibilities I have observed. First is both right hand derivative and left hand derivative exist and finite but not equal. Like previous example, in the mod case, you have left hand derivative as minus 1 and the right hand derivative as plus 1. Both are existing, both are finite but not equal. Then a function is not differentiable. For example, fx equal to mod x at x equal to 0. You can verify this condition. Second is one or both f dash a plus or f dash a minus or both are not finite, are not finite. Means one of them or at least one of them is tending to infinity, then the function is not differentiable at x equal to a. And the third is f dash a plus or f dash a minus or both does not exist. Means they are not existing even. Then in that case, the function is not differentiable at x equal to a. We have some important theorem and results based on differentiability, like continuity I've already discussed. First is sum, difference, multiplication, and quotient of two differentiable function at x equal to a is also differentiable. Second is if both fx and gx are not differentiable at x equal to a, then their sum or difference or product may or may not be differentiable. Means we cannot claim anything at x equal to a. Third is if you add a differentiable function, suppose f is differentiable and g is not differentiable function. F is differentiable and g is not differentiable. It is differentiable and it is non-differentiable. Then the output will be non-differentiable, like continuous. First one is continuous, second is not continuous, then the output will be not continuous. Similarly, in the differentiability, one is differentiable, another is non-differentiable, then the addition or subtraction will be not differentiable. But if both are not differentiable, then we cannot make any comment. For this statement. If we discuss the differentiability in any interval, differentiability of fx in closed interval a comma b. For all c belongs to inside this interval, open interval a comma b, the left hand derivative at c will be equal to the right hand derivative at c. But at boundaries we cannot make any claim. So we always find the differentiability in open interval, because the differentiability is not directional, not one-sided. So we will check the differentiability in open interval always. At the boundaries we cannot check the differentiability. At boundary x equal to a and b. Okay, we have some more examples related to differentiability. Discuss the differentiability of fx equal to mod x minus a at x equal to a. I have already discussed mod x at x equal to 0. If you put a equal to 0, you will get the same result. Discuss differentiability of fx equal to mod x minus a at x equal to a. You can check it is by graph also. I have told you the mod x minus a will look like, suppose a is any positive value, then it will look like this only. Then it will not be differentiable at x equal to a. But if you find by definition, then the right hand derivative will look like limit h tending to 0 f of a plus h minus fa over h, and it will be given as f of a plus h will be mod of a plus h minus a. You just put x equal to a plus h, minus fa will be a minus a. You put x equal to a here upon h, you will get limit h tending to 0 mod h minus 0 upon h. Limit h tending to 0 h upon h will be 1. Similarly, if you find the left hand derivative, it will be minus 1. And left hand derivative is not equal to the right hand derivative. So fx equal to mod x minus a is not differentiable at x equal to a. So where this function is going to be 0, the function will not be differentiable. Suppose someone asked you, write a function which is not differentiable at 3 points. Then you can give a simple example, mod x plus mod x minus 1 plus mod x minus 2. You can give any example. It is not differentiable at x equal to 0. It is not differentiable at x equal to 1. It is not differentiable at x equal to 2. So this function is not differentiable at 3 points. You can make 10 points, 5 points also. The function is not differentiable at countable number of points. Another example we have. Discuss the continuity and differentiability of fx equal to greatest integer at x belongs to integer. For x belongs to any integer, check continuity. Check continuity. Let any integer x equal to m is any arbitrary integer. So RHL will be x equal to m plus h. Then it will be limit h tending to 0 f of m plus h will be limit h tending to 0 greatest integer m plus h. If m is here, then m plus h will be here only. Then the left integer will be m again. Then the left integer will be m here. You can check by taking minus sign also. If m is negative, then you will get again m again. LHL will be x equal to m minus h. Then limit h tending to 0 f of m minus h equal to limit h tending to 0 greatest integer m minus h. M minus h will be here only. Then the left integer will be m minus 1 because m is integer. So left integer of m will be m minus 1. So you will get m minus 1. You can see that these limits are not equal when m is any integer value. When if you want to equate it, you will get 0 equal to minus 1, but it is not possible. It means the function is not continuous at integers. The function greatest integer is not continuous at integers. So I told you if a function is not continuous at any point, then it not be differentiable also. So fx equal to greatest integer x is not continuous at x belongs to an integer, hence not be differentiable at x belongs to any integer. You can see by graph also the function is jumping here. The jump discontinuity you will see. When a function is discontinuous, then it will not be differentiable also. Next example we have find B and C if fx is differentiable at x equal to 1 and fx is given as x less than equal to 1 and x square plus bx plus c when x is greater than 1. The function is giving you differentiable at x equal to 1. It means it is also given to you continuous at x. So use both the conditions, you can solve it, but we have a shortcut method also. You have two methods. You first check continuity at x equal to 1, put continuity condition at x equal to 1, then use differentiability condition at x equal to 1. Differentiability means derivative of one, left and right derivative both are equal. At continuity means the left hand limit and the right hand limit both are equal to the value of function at equal to 1. You can find the b and c, but we have a shortcut method because both are polynomials, so we can use directly for continuity. Given continuity at x equal to 1, put x equal to 1 in the both the limit, x in the neighborhood, left neighborhood and right neighborhood. If you put x equal to 1, you will get 1 equal to, if you put x equal to 1 here, because the function is given you as continuous, 1 plus b plus c. So you will get b plus c equal to 0, one equation between b and c. Now for differentiability, I am giving you some shortcut method here. You just differentiate it because both are both has derivative. Both the parts have this function have derivative. The derivative of x is 1 and the derivative of this will be 2x plus b. X less than equal to 1 and x greater than. Now put the derivative condition at x equal to 1. F dash 1 plus equal to f dash 1 minus. Don't write 1 minus, you will get from here only. And 1 plus, you put x equal to 1 here, you will get 2 plus b. So b will be minus 1. If b will be minus 1, then c will be 1. So if the function is given polynomial or any trigonometric logarithmic function which are continuous in the given respective domains, you know the property of continuous function, you can directly put the value in the case of continuous, left hand and right hand value. And in the case of differentiability, first you differentiate the first and second part, then you put the value. You will get answer directly. This is the shortcut method. Next example I have. Find ABC so that fx equal to a cos mod x plus b mod x plus c mod x cube. Find a, b, c, d plus d x mod x is differentiable at x equal to 0. See, I am seeing one by one function. Cos mod x. Cos mod x is cos x because cos minus theta is cos theta. It is a trigonometric function, is a differentiable in its domain. And what is the domain of this? Any real number. So cos x is differentiable for any value. It means this is a differentiable function. So we have no problem with a. It means a can be any real number. Because cos mod x is differentiable, so a can be any real number. We have no problem. What about mod x? Mod x is not differentiable. I've already told you at x equal to 0. So for making this function differentiable, we have to make this term 0. So how we can make this term 0? By putting b equal to 0. If b equal to 0, this term is going to be vanished and our differentiability condition will be fulfilled. So put b equal to 0. What about mod x? X mod x and mod x cube. See, x mod x can be written as x square when x is greater than 0 and minus x square when x is lesser than or equal to 0, or put equal sign both the equality, because at x equal to 0 the value is 0. Mod x is x when x is greater than 0. If you multiply, you will get x into x will be x square, and when x is less than 0 it will be minus x, the product will be minus x square. This function is a differentiable at x equal to 0. How you can verify? See, my shortcut method. The first method, you just go by definition, check the right hand derivative and left hand derivative at x equal to 0. You will get the values same. But we have a shortcut method. You just differentiate one time. You will get 2x. You will get minus 2x when x is greater than 0. When x is less than 0. Now I'm not putting sign 0 anywhere. Now put 0 This term will give you right hand derivative because x is greater than 0. So this value will be 0 at x equal to 0. And this value will also give you 0 at x equal to 0. Both are equal. It means function is differentiable. What about this is first time? We are one time differentiable. One time differentiable. If you check second time differentiability, we can see the second time differentiability also. Two time differentiable or not. Then it will be 2. It will be minus 2. Now if you put x equal to 0, this will be 2. If you put x equal to 0 here you will get minus 2. Both are not equal. It means this function is not differentiable two times. But we are interested in one time only. Not given, it means we are checking the differentiability one time only. So the x mod x is a differentiable function, one time differentiable function at x equal to 0, but not two time differentiability. But in the question, it is asked only differentiability, means if it is asked only differentiability, we have to check one time. We have to check one time differentiability only. So this function is a differentiable function. Therefore, d can be any real number. D can be any real number. Similarly, if you see the mod x cube can be written as mod x square into x. Then, sorry, mod x x into x. Mod x cube can be written as mod x square into mod x. And mod x square is nothing else x square. Then it will be x square mod x. Mod x cube can be written as mod x square into mod x. Then it can be written as x square into mod x. Now if you break x square into mod x, will look like x cube when x is positive and minus x cube when x is negative. I'm not putting 0 sign anywhere. You can put anywhere. You can put here also, because at x equal to 0, it is 0. Now check the first time differentiability. It will be 3x square minus 3x square. X is greater than equal to 0. We put 0 sign, equality 0 because both are 0. It means it is one time differentiable. Second time differentiability you check. So it will be 6x minus 6x. You can put equal sign because equality is satisfying here. You are again it is 0, again 0. It means second time differentiable. What about third time differentiability? It will be 6 minus 6. Now you cannot put equality sign at 0. Because at x greater than 0, right hand derivative is 6 and left hand derivative minus 6, both are not equal. So it is not third time differentiable. So for first time it is differentiable. It means C can be any real number in the previous question. C can be any real number here. Any real number. So can you make a function which is n time differentiable but not n plus 1 time? Can you make? Yes, we can make by taking this help. So fx equal to x to the power n mod x is n time differentiable function at x equal to 0. N belongs to any natural number here, but not differentiable at n plus 1 time. Not differentiable n plus 1th time. It is differentiable up to n time, but not differentiable on n plus 1th time. So it is a very important result. So these are some important problems I have discussed. In the next lecture, we will see the problem session based on limit, continuity and differentiability. That will be the very important and exciting lecture. Problem session on LCD, limit, continuity and differentiability. Okay, thank you.